Hey, it's me, Destin. Welcome to the second channel here. This is Smarter Every Day 2. This is the channel where I like to go deep into the weeds on the topics, like more technical detail, stuff like that. It's also where I'm a little more lax with the editing. So I hope you enjoy this. We're gonna be at Machina Labs, and we're gonna be learning about Roboforming, is what they call it. It's also known as incremental sheet forming, but we're gonna learn all about this process and how it works. If you enjoy this, the second channel, I'd appreciate it if you would consider supporting on Patreon. That'd be amazing. Or just, I don't know, subscribing to the second channel. This thing's been going for a while here, and it's slowly getting a larger and larger following, which is fun. But if you're into that, feel free to subscribe. If not, no big deal. Enjoy the tour with Ed and Bobak here at Machina Labs. Let's get to it. Okay, we're all mic'd up. So you're Ed, is that right?
Yes, Ed Mayer.
Ed Mayer, okay. Yeah. CEO, COO?
CEO.
CEO,
Yeah.
Okay. What's your background, man?
Engineering. As academically, I was a computer engineer. I spent early days mostly working on machine learning stuff, companies like Google, Microsoft. Ended up going to SpaceX eventually, and as a software engineer there, that's when I kind of realized all the challenges we had with manufacturing stuff and how hard it is to change geometry and design. After that, when I saw those challenges, got really excited about 3D printing, so joined, I think Bobby's coming too.
Oh, hey, what's up? Hey, I'm Destin.
Bobak, nice to meet you.
Nice to meet you, Bobak.
No,
cool.
Awesome. Perfect pronunciation, actually.
I've got a friend named Bobak. Yeah.
Oh, really?
Yeah. Okay, so now we have Bobak. Bobak, what's your title?
I head the technology partnerships at Machina.
Okay, so
he's also a co-founder.
A co-founder.
You're a co-founder. Yeah. Okay, so you guys made it happen.
Yeah.
And my understanding is I like machining and learning about stuff like that. Background mechanical, aerospace engineering. Yes. You're mechanical, computer science.
Computer. Yep.
What's your background?
Materials.
Oh, we're gonna talk. Okay, sounds great. So my understanding is you guys have a way to create shaped metal by forming it by, I don't know how to say it, touching it in a very special way is what I'll say. But but you come in and you I don't know, let me just draw it right here. So my understanding is you guys have a plane of metal, and you bring two tools in and you can touch the metal like that. And depending on the position of this, what do you call these tools?
We call them end effectors, but forming styluses, but yeah, end effector, forming end effectors.
Okay, got it. So these two end effectors, when they come in, drop my marker. So when these two end effectors come in and they put force right here, you can deform the steel in there. And if you do it in a certain way, I'm assuming, I haven't got here yet, but I'm assuming the position of this versus this matters.
Yes.
Okay, and so you can do things that are really interesting.
Yeah, so I think the best analogy that I can think of, how a potter, you have a clay on your kind of turning table, and the potter kind of pinches the clay with their finger and slowly deform it. That's what we're trying to do with sheet. But it's a very strong sheet, and requires thousands of newtons to deform it. But it's very similar. So the angle between these two tips, when they vary, it changes your wall angle. The amount of pinch force, how much force you're applying, also changes how much you're deforming the sheet. So where something complex happens between the two tips, it can be deformation with the pinch, it can be shear, it can be stretching. There's a combination of different mechanisms happening until it gets you a part that you want.
So you are playing in the really fun area of the stress strain curve. Like you're going past plastic deformation. And so my understanding, let's just go here. So let's say steel. So steel, we're gonna go up, and then we're gonna yield it, and then we do something like that. Is that right?
Yep, correct. Yep. Okay. Well, you're perfect at it. You know everything.
No, I don't know everything. So when you're pushing on a metal, you've got, which one is this? This is strain, right?
No, this is stress.
This is stress, okay? Stress.
Strain.
Strain. Okay, Bobak, I'm coming over and looking at you now. So stress strain curve, I'm gonna just give you that. So when we start deforming the metal, we get to right here and we get yield.
Correct.
And then we get permanent deformation right there, right?
Plastic deformation. But in theory, the plastic deformation starts even earlier, but on a macro scale, starts up there. And generally, as a rule of thumb, you do the 0.2%, let's say, type of thing. And then you define a yield for yourself. That's going to be my yield strength there.
So just by telling me that, I learned that you know a lot about fracture mechanics, right? because you start getting yields down here and stuff, right?
Yes.
Yeah. Okay. Okay. We're going to be able to talk. I think this is going to be really
I'm
fun.
glad.
So what do you do when you push these two end effectors in together? So I imagine you have many different things you can do. You can start mushing and molding the metal. That's the potter wheel or the potter metaphor, right?
Yeah, yes. You can either push them together, and then obviously like the area underneath expands, but they get thinner, the sheet gets thinner. But also like usually depending on the wall angle you have, usually have the tips actually slightly, let's say if you started forming, right? You usually have the tips slightly off. Right, you have a tip here and a tip here between the two wall angles. Right, they don't necessarily need to be on top of each other. Depending on what wall angle you're forming and how much you're thinning you're trying to create, you change the angle between the tips.
I see. So if, okay, I understand what you're saying. I have no idea how to point to this piece of metal and explain it, but I'm guessing you have tools we can look at.
We can see the robots downstairs doing the same thing.
Should we go do it?
Yeah, let's do it.
Does that work for you?
Yeah.
Oh yeah.
Okay,
Definitely.
cool. Here's your cap.
Yep, thank you.
Great. Thanks for being willing to jump in and go for it.
No.
Oh, of course,
This will be
It's
fun.
tough. You should, like, if you're interested, this is one of those. That
This is a cool thing. Yeah, you might want to let you know about this.
You should, like, this is austenitic sort of steel,
Okay.
so it's not magnetic. But then when you do the forming, because you're kind of changing how the metal is structured, then the formed areas are becoming magnetic.
How does that work? I don't.
So-
I guess I don't understand how a metal becomes magnetic.
So the amount of work you put into the metal induces some phase transformation into the metal, like your structure is essentially changing, and that makes the metal magnetic.
Really?
Yes.
Can you change that based on how you work the metal?
How much work you put in determines how much transformation you have, and then
Oh, it's a direct correlation.
correlation with that.
Oh, wow. I did not know that.
So that, in fact, if you look at some of your kitchen sinks and you put magnets in there, and if they're good quality and what, depending on, you would see that, oh, it's magnetic here, etc. So
Really?
it's a known phenomenon. So my fellow metals guys will say, oh yeah, that's strain-induced, transformation. So it's a well-known phenomenon, but now with this technology, you can actually control it.
Oh, really? You can dial it in.
You can dial.
Okay, that's pretty interesting. But these parts traditionally would be made with large. What do you call them? Molds or mandrels?
Yeah, dies or molds. Usually.
Dies?
Yeah.
Yeah. And
Well,
so-
some of them cannot be made using dies. So I mean, you have the video you have around stamping. So this one, if you make a mold for it, then this part gets stuck on a die,
oh, I see.
right? Because then there's going to be mold behind, and then you have an overhang angle here, so the die will.
Can you?
this part
Is this
in.
too heavy to pick up?
Yeah, no, pick it
no.
up. It's just 2 millimeter sheet.
Can you hold it right there,
Even
please?
say-
It's
This
even
one
thinner. Yeah,
is
this is 1 millimeter.
32,000.
Yeah. Oh, less than
32 thousandths.
Yeah.
So I see what you're saying. So it would get stuck on a die.
We get
Okay.
stuck on it. So now, with our technique, the robot can get into the part and actually form in the overhangs. And that allows you to do things that stamping cannot easily do.
Interesting.
Unless you create a very complicated die that falls, basically opens up into pieces afterwards. And
I
you can
see.
Take it out. Yeah.
I see. So you have access to more interesting geometries, but the trade-off is it takes a little more time to make the part.
It takes a little bit more time to make the part, but if you take into account the fact that you had to make a mold to make the part, then in a lot of cases, up to even thousands of parts, we're faster,
Really?
right? Because you can start making the part,
Really?
2 hours after your design is done. With the mold, you have to go through iterations on the mold, and usually the design of the mold is also slightly different than the design of the part, right? Because the sheet has a spring back. You stamp it, it comes off, it moves again.
Right.
So your mold is usually different than your actual geometry. It's just not the negative of your geometry, right? So you have to go multiple trials potentially on the mold. There's simulation software that helps you get close to what the mold needs to look like to get a certain part, but they're not super accurate. So for some complex geometries, you have to do multiple molds. So by the time you're going through those iterations, you're spending hundreds of thousands of dollars, you get your part, you might be even faster just forming with us. But then once you're forming the part, obviously we're slower than stamping. Stamping's a few seconds to get your part.
So this is great for development and low-rate initial production.
Yes, I think that's the first area that we're going after, but you were surprised where the break-even point is.
It's further down the
It's
chain
further
than you think.
than the chain you think. We were talking with Tesla a few weeks ago, and they spent $150 million on a stamping plant in Destin, right? So $150 million, meaning that like you have a very huge facility, the stamping presses, you have to have area for storage for dies. So once you start thinking about the full cost that it takes, all the equipment, machinery to die, and then the equivalent at how many cells can we buy with our technology, then the throughputs become very close.
Interesting.
Right? So, but you're right that it makes a lot more sense for lower volumes, and that's where we start, right?
Interesting. Yeah. I want to see the machines.
Yeah, let's go.
Can we do it? Yeah, let me grab my bag here.
That's actually, it's a funny thing. We're doing a special project. You're gonna know more about it soon, but we are forming a hood of a car over there.
The hood of a car.
Yeah.
I actually was reading up on this technology, and my understanding is I think Ford helped develop it a long time ago. Is that true, or is it a little different?
There's academic legacy, probably, I would say, 30 years of academic legacy. Some of those folks are actually advisor to our company, some of the bigger researchers in the field. Like Northwestern has been working on it. Some folks in Europe have been working on it. But then some corporations, like I think Ford, Boeing, Nissan did some R&D work in this. But nothing really commercialized out of those efforts. So we're kind of the first people who are bringing it commercially out there. And there are a few enablers we applied, like being able to model process using data as opposed to relying on physics-based simulation, using more cost-effective systems with robots as opposed to building very complex custom-made systems. So there are a few enablers we're adding to it that kind of made this possible in a
with
commercial
software
sense. And software, yes.
Yeah, and that's where you come in.
That's right.
Yeah. Okay.
So the software side is the other piece of it, which is one of the core enablers. Even though I come from a software background, I have been in manufacturing for a long time, right? So before this, I was at a company called Relativity Space. I was in charge of a 3D printing team that we.
Oh yeah. Familiar.
So been working on the intersection of robotics, software, AI, and manufacturing for the past 10, 15 years.
That's amazing. It's beautiful.
Yeah.
Like, how close can we get? Can we go toward the frame?
Yeah, let's go. I think that one is actually our design, our geometry, so you can show all of it.
So you're running KUKAs?
We run KUKAs at the moment. The robotic system is KUKA, but we also can use FANUCs. So you can see on the other side, those are FANUC robots.
Yep.
We are robot agnostic.
Those are, yeah.
We pretty much basically build the whole control system for the robots from scratch, so it's not dependent on any features that the KUKA has.
It's pretty difficult to film. Yeah, it's pretty cool. So, it's like a dance. Can I go talk to
of course.
this gentleman? I'm gonna look at this real quick. Oh, that's amazing. It's different than I thought. It's actually pushing. Sorry, I'm being rude. I'm Destin. Mark, what's up, man?
Nice to meet you.
Nice to meet you. How are you doing, man?
Doing well.
Is it okay?
I love your channel.
Oh, thanks. I appreciate that. I love your robots. It's pretty cool.
Yeah, they're pretty fun.
So you're Mark.
I am.
All right. So what's your background?
My background's in composites, actually, but Bobak recruited me and found me, and now I'm a robots guy.
Oh, really?
Yeah,
you
I
can
wasn't
switch just like
before.
that.
It was a steep learning curve, I think, but
Yeah.
it's been a couple years.
Can you show me what's happening over here?
Yeah. So this is incremental forming.
Yep. Incremental metal forming?
That's right. Yep. It's 2 millimeter aluminum sheet, and there's one robot on each side, and they're sort of pinching, and it's a lot like a potter's wheel, sort of like spinning like that. But here the tips are moving instead of the workpiece, and it doesn't have to be round, right? You can sort of push any shape you want, and so layer by layer, we're sort of stretching and pinching and pulling whatever shape I want here out of this metal.
So the triangle here is coming out of plane,
That's right.
which means this one over here, are there any optical lockouts I need to be aware of?
Nope, you can walk right up to it.
Can I walk here?
Yep.
All right, thanks.
Just try not to get between the robot and the sheet, you should be good.
Yes, sir. So this one is pushing.
That's right.
So do you have a force gauge on this end effector?
Yeah, there's load cells on both robots, so you can feel exactly what they're doing. Can I show that too, or
Sure.
can we keep it on the screen? Here, you
Okay.
can see over here what's going on.
So I could
So-
imagine.
Here's the workstation. This is the forces that both robots are feeling right now.
Okay, so can you tell me what colors are what?
Yeah, there's the Z component, the in-plane component, and then green is just the total.
Okay.
And so there's robot number 1 here is the one that's pushing, and then robot number 2 here is the support that's on the other side.
It's pretty easy to understand the forces pushing into the plate, but the in-plane forces are the side-to-side forces as the thing moves around.
What you could do is you could do this process with just one robot, and you could just sort of poke in metal and basically do a bunch of work by stretching.
But the boundary conditions, like, does it
Then you
work?
load the whole thing up in tension, right? So what we're doing by having a support robot on the other side is you pinch, and so you localize all the force just between the tips, which sort of reduces tension on the sheet and makes it so you can form a lot more accurately.
That's amazing. I'm sorry that I'm interrupting you because I'm just very excited and I realize I'm being rude, so I'm so sorry. All right, so if you were, can we talk about that over here?
Yeah.
So if you were to not have this robot and only have the other robot,
Yeah.
do they have names?
Sometimes. These don't have names yet. These are 1 and 2. But over there we have Jeffrey and Stumpy.
Okay.
And over there we have Thomas and Princess.
That's fantastic. Okay, so this is 1 and 2. So is this 2?
This is the support robot. This is robot 2.
The support robot.
Yeah.
Okay, so 1 is pushing, so I would expect a positive force or a compressive force on that one. And this one, if it was just holding in one position, would you just hold the robot here until it feels force from the other side so that you know that you are actually pinching?
We get pretty fancy about it. We're basically, should I talk about all this stuff? Am I allowed to do this?
Should I let him do it since
you wanna
it's
talk about it,
ultimately
Ed?
his authority?
No. I mean, I think Mark knows. Yes. Go ahead.
Ed,
No, continue.
Sure.
Yeah. It's just having.
Yeah, really there's control systems on both of these robots where we can sort of plan their nominal trajectory that just sort of is the theoretical what they should be doing. They also, they feel the forces, and we use that to update, to make corrections to the trajectory, basically.
Continuous feedback.
Yeah, so one of them is correcting for its own deflection under load because they're not infinitely stiff. The other one is trying to hit a target pinch force that we set.
Okay.
So it's an interesting combo, right? You're forming parts that are supposed to be in the end, like you're pinching a 0.5 millimeter sheet sometimes. I think this is a 2 millimeter sheet. So yeah, you have 2 robots on a pretty large envelope, right? So the envelope is 12 foot by 5 foot. Getting 2 industrial robots to be very accurate in this envelope is one task that we have to do through a lot of kind of calibration and proper kinematics. But then the moment they start touching the sheet will resist them. So, and these robots are pretty noodle. You can kind of imagine every joint slightly deflects, right? So there are controls and mechanisms that basically compensate for that deflection so that the robot stays accurate under dynamic load, right? Sometimes, depending on what sheet we are forming, it can be like 20,000 newtons of force that you're applying. It's like as high as the weight of a truck on a very small end effector on the forming side, right? So being able to, and under those loads, robots sometimes deflect 6-7 millimeters, right? And you want to pinch a sheet that's only 2 millimeters or 0.5 millimeter. So we have to adjust for that. So there's a control loop that uses the force data, some of the other data, to constantly figure out how it can stay accurate and pitch the sheet the right way.
But if can you give me an end effector with your finger like that, just straight up? So I can imagine if the 2 end effectors are coming in and touching each other, do they always stay perpendicular to each other or normal?
They depending on what wall angle they're forming and what is the thickness of the sheet, the whole angle radius between the tips is part of the forming process, depending on basically what wall angle you're trying to form.
But it is a sphere.
We have different types of tips. There's a sphere tip, there's a flat tip. Depending what kind of effect you want to get out of the part, you might want to use different end effector.
Different radii as well. If it's a sharp
radii.
crease, different.
Right.
Okay.
So that detects the smallest feature that you can do. Like you've done like a quarter an inch diameter for some very fine detail features. I think these are what?
3/4.
3/4? 3/4 an inch diameter. Yeah.
And what is the thickness of this plate again?
2 millimeters.
2 millimeters?
So like 80,000.
Wow. Can you tell me about the boundary conditions, I'll call it? I don't know what to call this, but the frame?
Yeah. So
Do you have a term?
yeah, we call it the fixture or the frame. Actually, you were right. We call it the frame, sheet filming frame. So you can see hydraulic clamps all around that just creates boundary condition for the sheet and holds it in place. We used to just use this with clamps, but we're going toward the future where it's automated. The robot can pick up a sheet with a suction cup, put it in the frame, then the clamps automatically close, hold the sheet, and then allows us for the sheet to not slip while we're trying to form.
That's amazing.
You can imagine in the future you can also play with this boundary condition a little bit to let a little bit of slippage, right?
Slippage or like deflect? I don't know. There's so much vocabulary here that I don't have, right? Yeah. So this is a hard thing.
So adjust the boundary condition. Essentially, you want to have a variable boundary condition to adjust and accommodate for what's happening during the forming process, essentially.
Got it. So you can control the amount of basic pressure you're putting on the sheet from the clamps.
Okay.
Yeah.
What do you call it when, if I were to take a sheet and I were to touch in the middle, I would get more deflection than the edge? Is that edge effects? Is that what that's called? Or
I think we call it like boundary condition effects.
That's what you guys call it?
Yeah, but you're right. That's just something that you have to account for. Boundary condition affects the accuracy of the parts that you get. So we have a whole software stack that tries to account for that, right? So you form a part, and then, so you can imagine, you form a part, you can then scan it. Actually, the same robot scans it afterwards.
To do quality?
To figure out, yes, exact quality, or to just figure out what it formed.
To update the model.
And then it will like, okay, I formed this. These are the areas that were off. That means maybe I should have pushed more in some areas and pushed less in some others. And you can manually iterate on that, keep generating data, and then later create a model that will tell you, okay, in order to form this geometry in this location in the sheet, you need to actually form a completely different part. And in the end, you can actually get the right part with all these things you talk about.
You might overshoot here, undershoot here,
yeah.
just like injection molding or something.
Yes.
All these processes have that.
Yes.
What is the benchy of this? You know, the benchy 3D print, the boat that you print when you're testing a 3D printer. Do you guys have an equivalent? Or
What is it, Mark?
Like a cone, a pyramid, little things.
Just a cone?
Yeah.
My favorite one is the face now, actually.
It just looks cool.
Yeah, it looks cool.
And so you guys will print that to test new software.
Yeah.
What are you optimizing?
We do all kinds of, we can't decide. We keep doing cool new ones.
What are you optimizing for? Like speed?
Everything. Accuracy, speed, surface finish. Yeah, all three at the same time is the hard part.
That's the holy grail.
Yeah.
Hey, nice talking to you, man. This
Likewise.
is awesome, dude.
Thank you.
I really appreciate it. Yeah.
And this is going to go to next week. It's going to get shipped to Chicago.
FabTech. I don't know if you've ever gone to FabTech trade show. It's like a lot of fabrication technology and machines.
FabTech?
It's like the biggest manufacturing show in the United States, probably, after IMTS.
You're telling me this now,
IMTS.
and it's next week, and now I want to go, and I can't go.
It's a nice show.
The same thing is going to go on a truck, get shipped back there.
Oh, really?
Yeah.
So no installation, pouring concrete. This whole thing is going to go.
Is this a big deal for you guys?
This is going to be a pretty big deal. So you can imagine all the other cells, if you look at it, they're all in concrete.
Yeah.
Right? And we had to actually, if you go around, you'll see the concrete that's under the cell.
Yeah.
Looks slightly different
Yeah, it's new.
than the rest.
You need a foundation for no vibration?
Yes, to just hold these things. Like I said, sometimes they apply its force as high as the weight of a truck. So
Got
all
it.
that forces goes into the foundation, right? And the regular warehouse is usually like 5 inches of like a 3,000 psi concrete if it's best. You have to do 13 inches of 5,000 psi concrete to just be able to, and with rebar and everything, to be able to counter the forces. With this new platform, we're completely decoupling foundational requirements. So you can put this actually this actually fits on the back of a lowboy, and you can kind of ship it anywhere in the United States. Yeah.
That's cool. That's very cool.
Yeah.
Man, this is mechanical engineer geek heaven. This is great. One thing that's interesting to me is you can see the whole sheet deform if you look very close.
There is like a deflection that you see, obviously, but then that's where the controls come in to accommodate for those.
What is the step over on this particular run?
0.6 millimeters.
0.6 millimeters.
Yeah, the face is 0.3. That's one of the many knobs we can turn.
I see. And so I assume the lower the step over, the better the surface finish.
That's right, yeah. But then it takes longer, It's just
You can
like
also
3D
have like
printing.
an adaptive kind of step over. So as opposed to machining where you go in kind of water lines, you can potentially say just fill the whole region, right?
Oh yeah.
So like when you go to a lower, shallower wall angles, just increase decrease the layer height. So you get more layers, and steeper wall angles have less.
Just like when you're doing CNC milling and you take a bigger bite, slower bite, whatever, or a smaller bite. That's cool. So that end effector, how much engineering went into that?
Ooh, we probably went through, I'll show you some of the designs, but we went through 6, 7 different designs for that end effector, from just being a static stylus to different types of coating that goes on the stylus, what the substrates look like, can it take the forces and not bend, is it gonna not shatter if we suddenly shock it, because it happens sometimes, and then does it need to move, do you need some kind of a bearing so that it reduces the friction forces. So we went through a bunch of designs. And this is actually designed, there's like 2 more designs beyond this that we have done. So this is actually 2 versions behind. So,
it took me a second to realize it's actually rolling, isn't it?
Yes. So this is specific one does. There are other ones that we have that roll in different ways.
Like a ballpoint pen?
Yes,
Yeah.
exactly.
So this one is just, I can't predict where it's going. Mark, you have a complicated program. So yeah, it's rolling along the pointing axis, I'll say.
Yeah, as you can see, like if it changes the wall angle, Z in plane Z also changes, right? The robot actually moves out of the plane and in plane.
Please explain that.
So the robot is not always in the same plane, right? As you're going in steeper wall angles, it basically moves around the forming tip.
I see. Yeah. So if you're, so what do you called it the wall angle?
Yeah. So like if with respect to the sheet, what is the angle of the forming angle? It's basically the complement of draft angle.
Okay.
Right.
I see.
Yeah.
That's awesome.
And you can see at the corners where it sort of changes wall angle, where the tip sort of goes in and out.
At the corners it changes?
Yeah. Like right here, sort of at the bottom of the part, you'll see it comes out now, and then it'll go back in.
Oh, so I see. So we're moving in the Z.
Yeah, like this wall is steeper than this wall, and now it gets steeper again. So the tip sort of goes in and out there to basically keep the tips perpendicular to the surface that you're forming.
Ah, I see. So even though it looks like it's a 2D operation on any one slice, it's actually a 3D operation the whole way around. So it's more, not a helix, but it's a, I don't know, I forget the Fusion 360 term for that. But
Does that have a term? I don't know.
I don't know.
Might be.
This one is,
Spiral.
they're planar slices, but the tips sort of move like this, sort of depending on the wall angle that you're forming.
Oh, really?
And we have some fancy non-planar slices too, if you want to talk about
I can show
that
you some
one.
of the parts too that are
Yeah.
non-planar.
Yeah.
So like you're forming on a curved section.
Yeah.
So now you're not starting from a flat sheet, you're forming from a section that's already have forming in it. Now your robot is actually going into a non-planar surface to deform and make another feature out of it.
Oh, that's awesome. Sweet. So this is what's going to happen?
Yeah, we're doing the face, and then this triangle is the one that's just started over there right now. This whole thing is about 90 minutes. Then it'll do this hexagon part. This one's actually a spiral rather than layers. Mm-hmm. So there's no...
Oh, I feel the oil.
It's a 1 millimeter pitch, but it's just a spiral the whole way.
Yeah.
And then all of these are actually chained together as a single operation. So the robots will do one, and they'll immediately go over and start the next one without slowing down or
That's
stopping.
interesting, because when I looked at it on the internet, I thought you were going to do one plane and then just move in the Z-axis and do more and more planes, but you don't have to do that.
We can do whatever we can imagine.
Yeah. Is it faster to do it, one feature at a time?
You can sort of hide the seam if there's no links. Like right here, there's a bit of a seam if you look really closely where we transition. But if I do a spiral, then you won't find that on this part.
You transition, meaning you move up.
Like this one is just planar slices. So you sort of do one loop and then you step in and you do the next loop.
Oh, I see.
The other one there is pathed as a spiral. So it's just a continuous sort of going a little bit deeper.
Is it also faster?
I guess a little bit because you don't have to turn around.
Uh-huh.
So yeah, that one, it just kind of goes the whole way.
That's awesome. Yeah, you're right. The face is cool.
Yeah, I like the face. Oh, you
You
might
know,
want
we
some
might have to
paper
give you
towels
a
now.
paper
It's,
towel.
It's all good.
it's not
Let's get you something,
dangerous
yeah.
or anything. It's
Sorry-
just,
sorry.
I get really greasy around here too.
We're good, Ed. You don't have to worry about
It's
it.
just right here.
Oh, okay. I will, thanks. Sorry about that.
Yeah, of course. This is actually an interesting thing. So like, I told you like the robots as we were forming, they apply a lot of force, and that sometimes causes them to deflect. So there's a period where we actually characterize the amount of deflection the robot gets in each joint, and that's a tracker.
Oh, yeah.
Measures the deflection, and that allows us to model the deflection and account.
To what accuracy?
We're constantly improving it. I think the total accuracy depends on the parts, really, because it comes down to also the spring back of the sheet. So there's like coupled with the material. So what we are measuring, I don't think we have measured recently how accurate the robot itself can be. I think the repeatability in the robot is 0.2 millimeters, so that's what we want to get to. But combined with the sheet, depending on the geometry, we can be as good as sometimes ±1 in a very large part, millimeters. Right?
You just blew my mind a little bit. There's a lot of math here.
Yeah.
So, is there a robot around this corner?
There's a robot, but it's not running at the moment. But
Can we walk up to it?
Yeah.
Okay. So, I'm gonna leave this here. So, I'll leave this here. Can I walk there?
Yeah, of course. It's a off cell.
So if I understand what you just said, like there's many ways to arrive at this point with this linkage.
Yes.
Okay.
Yes.
And if I arrive at this point and apply 5,000 pounds in that direction,
Right.
I'm going to get a certain radial deflection here.
Yes.
I'm going to get a certain radial deflection here.
On that joint.
And there. So what you just said is your code is, I don't know what the word is. Does the word holonomic systems mean anything to you?
Yes. Yes.
Okay. You have to also determine how you get there in order to anticipate the deflection.
Yes. Exactly. So I think what you're trying to say is that then there's two types of accuracy, like get the robot to one point, but then also accurately move from one point to another while the forces are changing on the robot. Is that what you were trying to get?
Yes, that's well, no, I wasn't thinking that far ahead. I was just thinking the first thing.
Yes.
So it's an incredibly complicated problem.
Right, yeah. I think it's basically bringing in dynamic load into equation of kinematics, right? So with the load, now there's an extra, like, okay, the joint A1 not only need to be at 60 degrees, they need to be at 60.1 or 60.2 degrees, depending if at the end effector is facing like a 5,000 pound force, right? And including that into the kinematic calculation.
That's hard.
Yeah, it's fun. It's a fun thing that our robotic team is working on.
Am I correct in saying, I'm not sure that this is true, but am I correct in saying, let's say I'm determining because of what I'm going to do.
Right.
This has to be at zero. Is this 0 degrees or 180? What is this?
The tip right now, you can say 0 degree.
0 degrees? So if this is at 0 degrees and I'm pushing into that, are there many different ways to set up the robot to get there, or is there only one way it can be set up?
So because we have 7 axes, there is probably there's unlimited ways to get to that point with different poses. Right.
So what do? Do you pick a few things and say this always has to be here, this always has to be here?
No, so there's so many cool things. You can just randomly choose, or you can optimize, for example, for stiffness in certain direction that your force is going to be. So you say, okay, move the robot and the rails so the joints are in the most stiffest combination to apply the most amount of force without deflection. So there's like you have a function to optimize at that point, right? And you can kind of part of your kinematics, you can figure out what you actually want to do.
You're wicked smart, dude.
No, I'm not.
Yeah, you guys are awesome. So was this an earlier version of the?
This was actually our first. This is our first cell. I think like the parts of this, our team welded this together. We were kind of just doing back of the envelope calculations, and
this was literally the first cell.
This is the first cell. It was funny because when we started the cell, we didn't have a lot of money, so we went to robot manufacturers, like, oh, let's sell this. Oh, it's 6 months lead time, and it's going to cost you, hundreds of thousands of dollars. So we ended up buying these robots from automotive manufacturers. These were the robots they want to throw away. They're like, reached the end of their lives. We don't need it anymore. So we bought them very cheaply, brought them in this facility. Since then, they have been putting twice the hours that they already had. They're still working, which is good.
This robot can actually move on a track.
This robot can move on a track. It's full 7 axis, both of them on both sides.
I'm in love with this place, man.
Those holes on the top, those are like early on, we're experimenting and we were like different part sizes, etc. So we didn't know what is it, like a generalized sort of a size that we can use. So it was like you have a magnetic drill drill holes. Oh, next part's coming in, it's smaller, let's drill a hole. Now that we have like a much better system, so you see.
Yeah.
So you love seeing this. There's a lot of nostalgia.
Turned into a Swiss cheese now, over time.
What do you feel when you see this cell versus the new ones?
I know, I think it's gonna come a long way, for sure. Those were days, I mean, we were literally sitting on the ground, putting holes in the concrete to put things on the ground. But it's kind of, the good thing is this cell is actually one of our most reliable cell even to this day.
Really?
Yeah, it just went through so many trials that it just works the smoothest.
You just know all the things.
Yeah.
So, and this is what are the names of these robots?
We ended up calling this one Stumpy and that one Jeffrey, because this Stumpy's a little bit shorter than Jeffrey.
What is, can you tell me about the end effector here? This is an earlier version, right?
Yeah, so
Can I stand here?
Yeah, of course. So the goal is, what we want to do is, even though we are doing sheet forming, really our long-term goal is to build what we call like a robotic craftsman, like a system that works like a craftsman. Like, you can pick up a forming tool, form it, drop the forming tool, pick up a scanner, scan it, drop the scanner, pick up a trimming tool. You can see there's a spindle there. So you can pick up a spindle.
This one?
Yeah.
And then that one too.
I don't understand it.
The last one.
Oh, down here at the bottom.
Yes. Both of them are a spindle. That one is at an angle.
Is that an ER20? That's like a Tormach head or something.
Yep.
What is?
Yep. Yeah, so the idea is you can easily change it. So you can see a tool changer here that can drop a tool, pick up another tool, and just move on to the next operation, right? And that's kind of we're imagining these robots really working like a craftsman that can pick up tools and do different things.
Okay, so you're not pushing you're applying electrical contacts and then you have the mill here.
Yep. So you can once you pick up, it automatically connects through the electrical contacts, and now the robot now has an milling end effector, and they can drop this, pick up the forming end effector, and go back to forming. Yeah.
Is this the current, what do you call this, the wrist or?
So this is the rest of the robot, but we call it the master tool changer. So it's the master and that's the slave. Basically the master picks up the slave.
So you have indexing pins to align it, and you also align on the plane. Mm-hmm. So you have total indexing. And then what's going on here?
So those are actually the bearings that through air pressure, they lock into the tool.
Okay.
So once it picks up the slave, this thing basically through air pressure come out and then lock into the tool so the tool will not fall.
Oh, that's amazing. Yeah. And what is this? You told me, but I forgot.
So there are different connections. So these are pneumatic connections and these are electrical connections.
Got it.
Yeah.
Will you show me the tools, or is this the best place for that, or should we do that somewhere else?
We can talk about the tools. I think, so you can see right now we do mostly forming and trimming. So we do mechanical trimming. So you can see that tool is in a spindle that allows us to cut the parts after we form them. And then you have different versions of a forming end effector. So that one doesn't have the final end effector that goes into it.
Okay.
It does the forming. The one next to it, it does.
This
so
one.
you can see that the end effector is right in there.
Okay.
And the robot can pick it up. Let me give you a.
It's really cool. Don't worry about the grease.
Yeah.
It's right here.
Yeah, you got it. Trying to get some of the.
So your tools, are they carbide, or is that too brittle?
So we tried a bunch of material. Right now, most of our tools are, the base of it is carbide, but then on top of it, we have a coating. That coating is slightly more complicated. We have tried a bunch of different things.
That's proprietary?
Yes. So
okay.
That's a coating that basically allows us to do form many parts without basically destroying the part or destroying the tool.
It's a pretty simple tool, isn't it?
Yes. So that's the end effector is pretty simple. This is one of our designs. We have multiple designs.
This
is one of the designs that we're working at the moment.
But then the coating, getting to that.
That's the secret sauce?
It took a while.
It took a while. 7 p.m. running to UPS, get this out,
And so is the goal that, I'm just going to ask a business question,
yes.
Feel free not to answer, but because you have the secret sauce on the tools, do you hope to sell the tools? Is that part of it?
Yeah, I mean, we basically the tool and all the holder, so that's just the end effector of the tool. There's all the other parts that goes into the tool that gives it some degrees of freedom. Yes, so as part of the business, we also provide the end effector.
And the perishables?
And the perishables and the consumables, yes. But yeah, I think even though that's a secret sauce, it really also comes down to the software pieces that we put together. And, without the software, if you get these tool robots to do some first heuristic path, like a machining, milling path, the part's going to be inches off.
Forgive me, I don't know what in this application, what does the word heuristic mean?
Like, for example, if you say get the robots and run them in, just, get the geometry, slice it in water lines, and start forming it. The final part is going to be inches off of what you actually want.
Really?
So you have to really account for a lot of different things. We talked a little bit about deflection of the sheet, spring back of the geometry itself, and then the fact that it can also tear. So if you don't put right amount of compression force between the tips, you might tear the sheet, right? So we get to the fracture limit and we tear the sheet. So combination of all those things are accounted in our software to get you a part that's going to be, very close to your final geometry and not like inches off. So that's, I think, where the real secret sauce is, the software piece. But
so
all
heuristic means like you take everything into account. Is that what that means?
No, what I meant when I said heuristic is that, like, if somebody buys a robot and says, okay, I'm going to do a milling path based on my heuristics, it's probably not going to give you a right path. If you just assume that, well, I'm going to do the most simplest thing that I can do, the part is going to be inches off. You have to actually do a very non-intuitive path.
I see.
To get to the right part. That's what I mean.
That's awesome. Yeah. Bobak, do you do finite element analysis on this stuff at the pinch point between the end effectors?
We started doing those back at the beginning. We use the off-the-shelf tools like Elestina, those type of things. Generally speaking, because you have to track the history of your forming and you cannot apply the usual boundary conditions, simplification, asymmetry, those type of things, your run times are going to become very kind of long, and the computation becomes very expensive to run those calculations. So we're doing work on accelerated ways of doing the calculations, developing surrogate models on top of the finite element package to be able to actually have fast running tools that we can actually run.
That's awesome.
The nice thing about our process is, as you're forming, you're going to gather all the data you need during the process, right? You can use those data to not necessarily do finite element models, right? But just build an empirical model, right? Instead of doing a finite element model and that would not be accurate and it's going to take computational time, just run a part, capture the data, and then over time, once you do thousands and thousands of parts, you can just use the data to have a high fidelity empirical model that's not based on physics laws. It's not a finite element model, but it's probably predicting it much better than finite element.
It's based on experience.
Yes.
It's like
that's why. Sorry, go ahead.
No, I was going to say that's the craftsman. That's kind of what Ed mentioned about the craftsman. Like back in the day, they were like, okay, work as an apprentice, learn how hard do they need to hit this thing, get that learning, and then actually, by the time they're there, they know, okay, I need to hit this steel this hard, this aluminum not as hard. There's that's the real sort of approach and the strength, because all that data is being collected.
That's rad. Can we go back over to the force gauges?
Sure.
Is that okay?
Yep.
Hey, real quick, just a little break here to say thank you to everybody that supports Smarter Every Day on Patreon. Patreon is the single biggest thing that supports Smarter Every Day and just makes it where everything levels out. Like I don't have to worry about month to month, like do we have a sponsor? How's it going? Smarter Every Day is supported by patrons in a huge, huge way. And I'm grateful for that stability that you bring to my life. And it's not for everybody, but if you are interested in that, you can check it out at patreon.com/smartereveryday. If you'd like to chip in on what Smarter Every Day is and the videos we kind of make, if you feel like this brings value to your life, then I'd be grateful if you'd consider that. If not, no big deal. I'm just excited to be exploring Roboforming with you here. This is amazing, isn't it? I think it's really, really cool. The software has to be incredible. So let's get back to talking with Ed and Bobak, and let's see what they have to say.
You're looking at the force diagram, right?
Is it running?
There's another part, we're doing the hood over there.
And also, just highlight that if you don't have like we have an on-site machine shop, that if you don't have that sort of agility in adopting and everything in terms of getting stuff done, like you wouldn't be able to move this fast. So like having that integration for us has been very key.
So it's a partnership between robotic manufacturing and traditional manufacturing. Is that what you mean?
It's like tools that we need. Like if we try something doesn't work, we go to our machine shop here. We're like, hey, let's change this angle and do that. Do it really quickly and rapidly, as opposed to having to wait to do it. So having that vertical integration within the company has been a challenge. It's key.
Super fast.
Fast.
All right, so this is another force, what do you call this? Force graph?
Yeah, so we're looking at the forces, the total force that the forming robot and the support robot. The forming robot is the robot that's pushing in the direction of deformation. The support robot is the second robot. So R1 is the forming robot, R2 is the support robot. You can see that.
One more time, please. I wasn't focused.
Yeah.
Can you point again?
Yeah, so R1, you can see it's a forming robot, and R2 is a support robot. Forming robot is the one that's pushing in the direction of the deformation, and support is trying to localize the deformation just to that area that you're trying to deform. So
Okay.
the full sheet doesn't globally deflect.
So maybe I didn't understand earlier with Mark when I thought I did. So it's always going to be positive deformation or positive force, right, on both robots.
Well, it depends on the frame of the. If you're talking about the sheet frame, one robot is forming in this direction, another one applying force in the direction.
I see.
So, basically, the forces from the robot should basically match the forces from the other robot plus the forces that goes into the clamps, right? So this one robot is always applying slightly less force than the other.
So it's a complicated free body diagram because you have planar deformation involved.
Yes.
And not only do you have planar deformation involved, you have planar deformation with a weird looking shape.
Right.
And so that's why it's so hard.
Yes. And that's why we also rely on empirical modeling as opposed to try to understand the physics to a very small detail. We understand it as much as we can, but at the end of the day, it comes down, form the part, capture the data, and empirically model what's happening, as opposed to try to really wrap your head around all the details that's going on. Because between the tips, I would say all three mechanisms of deformation is happening. You have a little bit of shear, you have a little bit of stretching, you have all three, right? So
The three being?
it's just shear,
Like the tension,
compression, and shear.
Tension, compression,
Yeah.
shear. Okay. Can I see what this one's doing real quick? And then I'll come back and see if I understand this better. What is the thickness of this?
So this is a 2 millimeter aluminum sheet. We are forming a custom hood for a custom truck.
Custom hood for a custom truck. Whose truck? Is it your truck?
Well,
You don't have to say.
This is a secret project that's going to come out. So
Okay, got it. Or is it? Is it okay to show that we're doing it?
yeah, you can show the track, but I was just saying you will. It's a full vehicle project that's gonna come out at some point.
Okay, Ed. Question. This robot's stationary. This robot has an additional axis.
The answer is embarrassing. So this is our second manufacturing cell.
Why is that embarrassing?
Well, I'll tell you. So this is our second manufacturing cell. We still didn't have enough money to buy new robots, so we bought them used. And at the time, we couldn't find a rail in the market, so we just welded that and put it on a pedestal. That's why it's called Princess, because it's on a pedestal.
Princess is on a pedestal. All right, you guys are likable. That is massive. That's massive.
So this, I don't know if you've seen Titans. This robot's called Titan, the model of it, and they can apply as high as 20,000 newtons of force.
Really?
Yeah. So sometimes when we do very thick sheets, we're doing like 3 or 4 millimeter steel. It can basically applies up to 20,000 newtons to deform the sheet.
That's crazy.
Yeah.
So I noticed it's going a lot slower on this thicker metal.
It's going slower because this is on an older version of the software.
It's
Okay.
the same thickness as that one that you saw.
Oh, is
Same
it?
thing as-
It's the same thickness.
But in this specific sheet, these robots can do much thicker. But this one is the same thickness. We are on V1. That one is on V2. So the controls have improved on that one. So
Really?
it can go faster. Yeah.
That's amazing. That you've upgraded that much because it's fast over there.
Yes, it's all about like figuring out how fast you can kind of command the joints under dynamic load without over torquing them, and kind of optimizing that. Get to the point where you can have maximum acceleration without over torquing the joints as the load on the tip is also changing all the time.
Can you please say that again?
It's all about maximizing the acceleration you can get at the tip, at the end effector, without getting an over torque on the motors, right? So in the earlier versions, we would be very conservative because we couldn't do that calculation of what would be the maximum torque I can apply to this motor while I maintain the accuracy. So with the new version, now we do those calculations. So we go as fast as we can and apply as much as the acceleration that we can at the end effector, basically pushing the motors to its limit before it over torques.
So does that mean that the software is robot specific because you know the torque limits on each motor, or is it parametric in that you can
It is
load?
parametric.
Okay.
Yeah.
The reason I keep flanking you like this is because I'm keeping you and the robot in the frame.
Oh, I see.
I'm
So
not
you
being
want-
awkward.
no,
That's what I'm doing.
Yeah, let me know. Sometimes I feel like maybe you're asking me to get out of there.
No, I just figured I'd just come out and tell you what I was doing because it's like I'm just trying to sneak behind you or something. Sorry about that. So it is parametric. So you load each individual robot, and you have torque limits on each robot so you have a robot model. You have a I guess we call this the model.
Yes.
Model has different features.
Yes.
And then do you also have to build in I guess you have to have two robots.
Yes.
Because I've seen this done without a second robot where you just have like a rubber pad on the bottom, and then in that case it actually is only Z-axis.
Yes.
Is that true?
Yeah, so in that case, you have only one robot and then you can push it against the pad. In our experience, that doesn't produce accurate parts. You cannot properly localize the deformation. Like I said, it's really a tricky dance between the two robots, being able to get into the right angle with respect to each other, depending on what feature they're trying to form. And then depending on how thick the sheet is, they need to counter even with more force. The support robot needs to counter even with more force in a very surgical manner. So we have noticed that when you try to be like form it against a kind of rubber or something, the part just doesn't end up being very accurate.
Because you always have a fixed force on the other side. Well, I mean, is it Hooke's law applies on the other side?
They probably have some kind of, I think it's actually probably a little bit complicated because the rubber is usually probably applying a little bit of compression on all sides. Yeah, I've never fully thought about it, but we realized that it's just you can't get very accurate.
What I like about you guys is you're like, you can do all the math, you can do all this crazy stuff, but in the end, it's gonna do what it's gonna do.
Yes.
So let's just go rip something up and get that data and then fold it back in and then
Right.
lather, rinse, repeat.
Yes.
Do it. That's like, and I would give kudos to Ed. He's really like, okay, let's do it. You know, you can't go and kind of try to figure out, oh, let me figure out the forces. But it's so much informative when you do the actual part and kind of fix the problems, issues, and then, okay, next one, and capture those learnings.
Yeah, I remember like early days, we took the whole team to I don't know if you know Bobby Walden. He's like a very famous sheet shaper. So he shaped sheep sheets with hammer, right?
Okay.
So he holds up a sheet, goes on there, power hammer, hammers it into shape. He does a lot of custom panels for like hot rods and old cars. And I remember early days, there's somebody I knew for a long time, actually like worked in his shop for a little bit. I was like, okay, like we're forming this company, we had the early team, I'm like, let's get him into his shop. And these guys hammer sheet with their hand to really understand what's going on. Because at the end of the day, I think the material does what it does. And if you think, and then there's variances between batches of the material. Some have higher strength, some have lower strength. So you gotta be adaptable. And a system who can just look at what it did and constantly improve, that's a system that's gonna win. That's why humans still can do sheet shaping. It was very tough for static systems to do it other than humans, right?
So you guys just don't suffer from analysis by paralysis. What am I saying that? What is it?
Analysis paralysis.
Analysis paralysis?
Yeah.
You just don't do that. You're like, go.
Hopefully.
Yeah.
I mean, we want to be intentional and thoughtful about it as well, but I think there's a lot of unknown unknowns when you step into physical world and you start getting those and understand those as you go through them. Yeah.
That's great. Yeah. Man, I feel stupid because I've been waiting my whole life to say paralysis by analysis and I botched it, but it is what it is. Dude, this is awesome, man. How long will it take to make a part like this? Can I go right here?
Yeah, just yeah, I think that would be good. I think that it's not gonna. You can see how much far it comes back, and then
I won't right here.
Yeah, I think it should. Oh yeah, you can kind of see the line actually.
I'll just let it come to me here.
So depending on the full frame. So this is a 10-foot frame. Right now, this one is going very slow. So this one takes probably 15 hours to finish. But we have done a full frame with the newer version of the robot in less than 5-6 hours.
So when you get done with this thing, you're gonna have a fully formed sheet. This is gonna be a hood for a truck.
Yes.
It'll be done. How do you get it out of that? Do you like jigsaw it out, or?
So the same robot, after it's forming it, scans it, and then maps the scan to the trimming path. So it aligns the trimming path to the scan the best way, picks up a trimming end effector, and trims the part out.
But once you start, let's say I start trimming it, that's a heavy part.
Mm-hmm.
How do I not drop it? Does the other robot hold it while it?
So that's maybe something we can do in the future. For now, what we do is we leave few tabs in. So you leave few tabs around the part, and then technicians come in and cut the few tabs and take it out. But we want to make sure the robot at least does the accurate cutting, so that the part
Before you remove it.
Before you remove it, and then you leave few tabs in, and then you cut those tabs and clean those tabs out.
Dude, it's really cool. Yeah. Do you give a lot of you give a whole lot of tours, don't you?
Not actually a whole lot.
Really?
Yeah, I think we have been like really heads down for a while, and then I think just more recently, as we are kind of expanding the operation, I think we have been, we have been asking people to come and see that. Most of our customers, even our customers, when we have done parts for them, when they come here, they're like, this is a much bigger robot than I thought. In the video, it looked like it was pretty small. And they come here, it's like 30 foot by 30 foot stack.
Can you hold this?
Yeah.
Can we use it? I'm just gonna show how big it is. It's big. Thanks. Yeah, that tells the scale. Bobak, can you take me to the metal, like your stock? Like, do you have sheet stock somewhere?
Yeah. There's some here. They're like distributed all over the place, but these are the ones that have been.
Of course.
These are the ones that we've cut to blank to the size that we want to do for the customers, and they're ready to go. And everything is, labeled, so that we can have full traceability from the start to the end of the part.
Will you tell me the difference? Is this galvanized?
This one seems to be, yes. This is the galvanized steel, yes.
So will you tell me the difference in working galvanized versus aluminum versus stainless? I mean, are there different things that you have to take into account?
So the amount of like a pinch that you apply, the kind of the rate that you form. So we've started forming, for example, like in the other extreme, like titanium, and you do that at room temperature. Maybe you have to like go slower for those type of metals with the forces that are involved compared to like that 2mm aluminum or the one that you saw earlier. That's kind of like those type of that's where the function of the metal itself. Now, if you have like a galvanized steel where you have to be conscious of the coating that you have on the metal, then you have to also think about like what type of end effector do you use for that, so that you don't damage the coating as much.
So if you had titanium and you have the ability to cut, you have a trimming end effector, you called it. Like back in the day when they were building the SR-71, they didn't know how to work titanium.
Right. Yes.
I saw the glimmer in your eye.
To this day, I don't think they can easily work titanium.
Really?
Yeah, I think it's a very tough alloy to work. I mean, we figured out how to machine it, but still forming it is very tough. Unless you elevate temperatures, and room temperature is really tough to form titanium.
But in theory, could you use this technology to form it and then go in and cut the rivet holes?
Yes.
And are you very excited about that?
I think those are the areas that we are the most excited. Like enabling alloys that were just impossible before. I think, for example, for hypersonic, you said SR-71, but all the hypersonic applications as the focus of attention a lot now with some of our customers. They have a very hard time forming skin of these aircrafts out of high temperature alloys, titanium, Inconel. We're talking about refractory alloys, and we're excited to be able to just form and cut in one shot without having to spend hundreds of millions of dollars in, let's say, super plastic forming equipment. Yeah.
Okay, so
Do we have a titanium part? We can actually show you probably.
Yes, so let me
Do?
find.
yeah, let's do it.
I
yeah.
do have.
I think that's we just want to make sure it's a part that's not a customer part.
Yeah, that's the.
But I
that
think we
was,
have
I
few.
have the nickel one, but that's a customer part.
I think we have something that might.
I'm pointing the cameras at the ground so I don't see anything. Can I follow you?
Yeah, please.
Here is fine.
Can I? What is this
By the way,
for?
this is our assembly room. So we assemble the frames, the electronics, the tool changers. So this is where we assemble all the different pieces that goes into the cell.
Oh, that's awesome. So
Let me actually-
these
I
are the
have-
clamps.
So these are the clamps. Yes. So we machine
Is
them
that
all.
steel?
Yes, the clamps are steel,
Water jet.
water jet, and I think and then they coated them, they anodized them, they powder coat them, and then
I go grab some titanium for you.
Is it okay if I look at this stuff?
yeah, so you can kind of see there are different end effectors.
Is it a thrust bearing?
No, that one I think is there. So that's a needle bearing for one of our end effectors.
If you would prefer, I don't show stuff. Just
No, we can probably look at it in the end. I think
Yeah, sounds-
people. This is going to be outside anyway, but you can see this is a bigger tool, and you can see a needle bearing inside of it.
Yep.
Yeah. So
That's interesting. I would have expected a thrust bearing there. Yeah.
yeah. So I think maybe you should talk to our engineering team. You should get some of your advice. That would be great.
Oh no, that's interesting.
And you can kind of see. So these are actually. So we know how we talked about. We create different. There's different versions of the tool. So we kind of. This is for the ballpoint version. This is how we kind of measure and grind the tool down. So we have our own grinder. So we build everything. We said like the tools are all built here.
Oh man.
Yeah.
You can make custom carbide tools.
Yes.
Is it? Oh, that's awesome. So when I saw the video, I didn't think you were actually rolling. I thought you were pop, 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 pop. I thought you
Yeah,
were
like hammering it.
Yeah. Can you do that as well?
You could. Actually, it's one of our plans down the road is as we are going with the thicker sheets and higher strength sheets, how can we bring the yield of the sheet down? One way is ultrasonic. Like you maybe can apply some kinetic energy to bring the yield down. Or you can locally heat it.
So you
Right,
can
as you're
vibrate the sheet as you're working it? Is that what you're saying?
Yeah, basically just like same as hammering, but like much faster and much basically get to the kind of ultrasonic kind of frequency to hit the sheet
With the end effector.
with the end effector.
Golly, man.
Yeah,
I
and
like
it
you,
allows you to go to the higher strength.
Ed, you're one of the most fascinating people I've ever met.
Oh no,
Is this titanium?
This is
That's already
titanium.
cut out. The part from the customer cut out, but you can see kind of the rest of the sheet. It's actually a pretty thin sheet, super strong.
How much does a sheet of titanium like this cost?
Oof, this one is expensive.
Okay, enough said. That's incredible. And so why did this is all not part of the part, but this was kind of like the form, I don't know what the word is.
I think they.
Can we set it up here, please?
Yeah, and I think the good analogy for folks who are like familiar with 3D printing
Support.
is a support structure for a formed part.
Interesting. And
Right.
you do that for what reason?
So we do that so that basically we have we create enough stiffness around the part that as we are forming it, the part is not buckling,
Got it.
right?
Okay, so because I'm pushing here. Okay, wow, that makes sense. Because if I'm pushing right here, so steeper angles give more rigid parts.
Yes. And the deeper it is, it becomes rigid.
He just
more
looked
rigid.
at me. He just,
No,
yeah.
like that
That's right.
explains.
And the
yeah.
deeper it gets, also you are more rigid because you have to overcome a little bit of elastic deformation before you get to plastic.
Yeah.
So like if you want to do a very shallow part, it just doesn't work. You're just gonna push the part in and out. Once you go further deep, then you create more rigidity. You can easily overcome the initial elasticity and get to plastic regime faster. Right.
My brain's on fire. So, can I try to say what you said, but I don't have the words you do?
No, go for it.
So like if I have a sheet like this and I push right here, it's going to deflect.
Yes.
Because of like the what is it? It's cosine or tangent.
Yes.
It's tangent, right? So it's going to deflect easier. You have more planar deformation. But if I can rock that up, the more I go like this, I'm going to be in straight up compression.
Yes.
But I can't do that because I'll buckle the sheet.
Yes.
So I have to find an optimized position that's best for the part.
Yes.
And also, you're probably doing stuff about toolpath too.
Yes. Yes.
Is that how you do it?
Yep. now you can start seeing how this whole design space around the part also affects the accuracy of the part, right? So you can start thinking about how you can generatively come up with this design space.
Using the empirical model.
Empirical model to come up with something that's going to give you the best results, right? You want certain stiffness in certain direction because the parts have its own stiffness kind of properties. Yeah. So the idea is like, once you have all the data, you can combine all these things to come up exactly, automatically suggest to you what the skirt needs to be like.
Have you taken, this is a dumb question, but I don't really understand what it does to the material, because the material has to flow.
Yep.
Maybe flow is not the word, but it has to move.
Flow is the right word.
Flow is the right word? So if I'm making, have you taken a plane and then done a sweep like that, and then did dog bones along the way to see what it does to...
Yes. I think that's work that Robotic have been doing with some of our bigger
Are you allowed
customers.
to talk about that?
Just general terms, like we were benchmarking some, not titanium necessarily, not yet, but benchmarking against hydroforming, some aerospace grade aluminums. And we did form the same geometry using our process, our roboformed sort of a geometry and a hydroform process. And we took dog bones with an independent sort of a
tension test on each spot?
Tension, hardness.
And like you said, it was like different wall angles, different directions, so you can kind of characterize how much work hardening you put in into each, depending on the direction and the wall angle. Like you said, like, you can create a kind of almost a
sweep.
What do you call it? Is that a? As a geometrical name now, it's where like it's constantly increasing.
A logarithmic?
Yes.
Or something exponential, I don't know.
It's on the name
I
for
know,
it.
like
I forgot. Anyway, but yeah, getting different wall angles so you can see how much work hardening you're getting based on your wall angle.
That's amazing.
Right.
And so, did you get any information out of it that you're willing to talk about?
No, it's funny. Like early on, we were asked, customers were kind of had experience with 3D printing. 3D printing, if you ask, like if you had 3D printed this part and you had asked like us, like, hey, what's the properties there? I'm like, I don't know, where was it printed? Which location in the chamber, all that stuff. With this process, you're working the metal. You're working the metal be more than this, so the strength is gonna be higher. And in metals, like you generally increase the strength, your elongation, ductility comes down. So the general outcome was, with our process, you work the metal more, so the strength is higher at the end of the forming, let's say compared to hydroforming or stamping, but then your elongation is going to be lower from that. Yeah. And that was generally for the aluminums, where like you're 20 to 30% stronger using our process to make the part. Obviously, your elongation and the amount of energy that you can absorb with the system might be lower.
Okay, so please explain hydroforming, because I was shaking my head, but I'm not 1,000% sure I understand hydroforming. So is that a competitive process?
It is yes and no. It is a process where you do need a tool or a die to make the parts. So our process, you don't need anything. You just have those in effect. So you do need that tool, whether you have a bladder on top of it or not. So you would have the fluid on the top with the bladder. You put the metal there, you press, and you kind of conform to the shape of the die, that tool.
Think of it stamping, except one side is fluid pressure.
Okay.
Right, so you're pushing against the die with fluid.
I see.
So it's a whole process. I think it's a process that like people try to use when they want to get rid of at least one die.
I see.
And sometimes it allows you to do a deeper draw, depending on the alloy and the geometry. But in this specific case, the customer wanted to replace our process with that. So we kind of did some of the tensile sample tests, benchmarked it against that.
I see.
Yeah.
So with hydroforming,
yes,
you have a die on one side, just like you said, and then you have that bladder, or I've even heard of explosive hydroforming, but you still have to machine that die.
Yes.
And what you're saying is you don't have to do any of that. It's all software load.
Yes.
So as you develop a faster routine with your software toolpath, you have the ability to get to prototype faster. Is that true?
Yes. So, I mean, you get your first part hours after your design is done here. With hydroforming, you still have to go through die design. Like, your part is one thing, now you have to design your die, manufacture your die, go through multiple iterations, because every time your die is basically not giving you the right part, now go machine another die, versus with us is just change the software parameters and go again. So you usually get like, even with hydroforming, I think the fastest customers we have had, we work with SpaceX, for example, or like one of the fastest out there, like trying to really push the vendors to get to the parts fast. Like 2 to 3 months at least before you get to your parts. Yeah.
And you're doing it in a day.
Yeah, in a day you can be done. I mean, there was like parts that we got from customers. They send us an order at like 2 p.m. and then 10:30 the parts started running. 10:30 at night the parts start running. The next day we have the part.
Yeah, that's something to be proud of. Okay, so if I'm looking at this sheet right here, is the material the thickest it will ever be right here in the plane? And anytime I work, I'm having to move material, so it's going to be thinner.
Yes.
Here, is that true?
Yes. So I think the good law you want to apply is that kind of conservation of volume, right? So as you're going on a higher wall angle, the cosine of your wall angle, or sine of your draft angle, times the original thickness roughly gives you the thickness you're going to get in the part.
Can you say that slower, please?
So cosine of the wall angle, or the sine of the draft angle, times the original thickness of the sheet, will give you the thickness you should nominally get in that situation. Obviously, it depends on the material properties and how it flows, but roughly that gets you there. But this is only if you almost form the part in water lines. So I can show you some other parts. If you form the part in stages,
that's what I was about
then
to
you
say.
can play.
So if you were to push, if I were to start right here and I would just push up,
yes,
then I would have parts of it that would still be thick there. And basically, if you go deep first, you could make a thin wall angle.
Yes.
And then you could have thicker features at the bottom. Is that right?
Yes. Actually, let's go. I'll show you I can show you on a whiteboard. Okay. So you can imagine. So you originally have a sheet, right? And you have certain thickness. Let's say we call it T.
Okay.
And then you're forming the part. So that same part now, it has something like this, right?
Yeah.
So now you have this alpha angle. This was T, and this is T prime. You can kind of, if you do simple trigonometry, T prime is cosine alpha times T.
Okay.
Right? But to your point, in reality, what ended up happening is this is T, and this is not this gradually.
So
happens.
just 1 second. Let me look at this. So T prime is this or this?
T prime is this thickness. T is this thickness.
Okay, got it. Yep.
Right? And this is obviously alpha.
And that's if you start working it from here and you're drawing it as you go.
Slowly pulling it out. Right?
Yeah, but if I were to start here and push there, then I would expect this to remain thick.
So in reality, even when you do this, you usually have a little bit of, in reality, can I cut?
Do your thing.
So in reality, it actually looks like this, right? And then you get thin, and then you get thicker again at the end, and this is going to become your T prime. So you have a little bit of thick and thick on both sides.
Yeah.
But, so what I was going to say, but again, the just law generally applies, but instead of forming, if I form this way, that's what I'm going to get. If I form it, let's say I go and form, first I form, in order to form that wall angle, first I form something like this. And this is, let's say, alpha. And then I form this wall into this. So push this out. And this is becomes...
So you would bring the end effector normal to the wall and then
push it out.
So it becomes a three-dimensional break.
It becomes a three-dimensional break. Or even like if I waterline this out, not necessarily just push in, waterline this, form it out, right? Like start from here and assume this is now my second forming surface and start forming that, and this becomes beta. Then this thickness in the end, this T, will become T, initial T, times cosine alpha, cosine beta, which means that you can actually control the thinning depending on what stages you're going to have in your forming process.
That's the first bend and that's the second bend.
That's the second bend. So yes, and then cosine alpha, cosine beta is usually smaller than cosine alpha plus beta. So now you control thinning, right? You're now actually thinning the material less.
But it depends on the order that you got there.
Yes, yes.
That's fascinating.
So a lot of, we call this actually restriking. So
Restriking?
Yeah, you strike the part, restrike it then to another shape, and now you're distributing thickness a little bit better. So the part doesn't thin if you're doing a very high wall angle.
So why would you want to do that? Why would you want a thicker wall thickness? Why? You see what I'm trying to say?
Yes.
If you have a high angle, the wall thickness probably doesn't have to be incredibly thick.
The problem is, so what is cosine of 90?
Cosine 0, 1, cosine 90, 0.
90, 0. So that means that if I push this to a 90-degree wall angle, I'm gonna have 0. This is gonna tear.
Ah, I see.
Right? So in order to be able to do 90 and overhangs, then you have to go in multiple stages to distribute the thickness a little bit better.
So you're managing, it's also going to determine whether it's shear or whether it's tension as well.
Yes.
And so you have to look at more circle.
Yep.
More circle?
More circle, yeah.
2D or 3D more circle?
This is 3D.
So could you do another thing? Could I restrike, make a plane here, and then instead of having a tool right here, could you ever have a situation where you bring a whole end effector over that's like a plate?
Yes.
Or like a line, and then you could actually truly do a 3D break?
Yes.
Can you do things like that?
So you're actually touching up on the right thing. That's why we were talking about the PhD in mechanical engineering. So to do a proper bend, you need 3 points. You
Yes.
only have 2 points. So yes, if you really want to constrain it, then you need a line or something that gives you 3 points. We haven't done that. I think our goal is really stick with the idea of like, you only have 2 points, figure out the math, figure out the model that gets you the right thing. Because the least amount of tools that we have, the more flexible the system is, right? If I can get away from not having some custom end effector on the other end, that's gonna be a line or a plate, then the more easy it is for me to be more flexible, right? If you have like a tool tray of like 20, 30 different tools, it becomes a little bit more complicated and economically starts to not make sense sometimes.
Got it. But in like the far distant future,
Yes.
I could see where you would have a rivet gun somewhere on an end effector,
Right.
or you would have a way to put in PIM nuts and,
Yes.
and things like that. Are you working towards that, or
Yes.
we're not quite there yet?
We do we can do different processes. We already do forming and trimming and scanning. We can think about surface finishing, we think about riveting. We can even do additive, like add a welder to it, do some additive features on top of that. We started from sheet metal because I think sheet metal is just like the largest metal processing sector today, right? So there's a lot of need. But yes, no, we can do other processes in the end as well, but hopefully we can have tools that are not very geometry specific as much as we can, right?
That's awesome. So what's special about how you do the titanium?
The titanium, generally to form it, you do need to go to elevated temperatures because titanium doesn't like to be shaped. The way we're doing it, because of the stresses that you have imposed on the metal, you can actually do it at room temperature. So
And that's a big deal.
it's a big deal. Because then if you go to elevated temperatures, you need special molds that can work at high temperatures. You need a lot of energy intensive service systems, all that stuff.
So it's process optimization.
It's process optimization, but again, enabling something new. Not like now you don't have to, you can change your design, but you don't have to worry about like a expensive temperature dependent services.
That's amazing.
Awesome.
And thanks, Babak.
No, thank you. Appreciate it.
So Mark has figured out how to get my GoPro clamp on this thing so we can see.
Sneak through here if you
Yeah,
want.
how did you
I'm
do
gonna
it?
put it like right on here, like this,
Okay,
so you can see the tip.
so we can ride along.
Yeah.
And so this would be the convex side. No, concave, excuse me. All right, so go ahead and can you start the GoPro? So Mark's figured out how to get this on there. Okay,
That's
great.
fun.
Can we see the tip?
I think so, yeah.
Okay, great.
Cool.
All right, we'll back up. We'll see what that looks like.
All right, should I resume it?
Let me, yep.
Hold on. I might have to like manually restart this thing. This is actually cool. You'll get to see the whole thing start sort of from the beginning. And bear
Okay,
with
he's
me
doing
for a
another
couple
startup
seconds here.
routine real quick. So does it have to, you have to calibrate it when it starts?
I'm gonna manually retract it and sort of bring it back into the home position, and then we'll start the next one. I'm just kind of backing out of this part here.
So you're controlling, is that the Z-axis?
That's right, yeah, I'm just going in positive Z right now. I'm just manually driving this thing. And manually, I usually like to go nice and slow. It's just so I don't, you know, crash it or anything. I'm gonna go this way a little bit. This is the positive X direction, so you can see it's parallel to the sheet.
Yep.
Might retract a little bit more.
In Z?
This is in Z, yep. Now I'm gonna switch it into automatic mode. I'm gonna send it to the home position. It's gonna sort of twist and go up here. I can stop it at any moment, don't be too nervous.
Okay.
All right.
And so you're just observing so you don't crash?
Yeah, I'm just watching it. I know what it's gonna do, but just to be safe.
Safety, yeah.
Yeah, yeah. All right, so this here's sort of the home position. All right, that one's set up. Now I have to do the other one real quick.
Yep. And that's like
All the way around
standard
the other
industrial
side.
robot stuff you're doing right now?
Yeah. There's generally sort of 3 different ways that I can operate this thing. I can jog it around manually like I'm doing right now. I'm gonna back up so I can sort of see it. There's,
How long did it take you to learn industrial robots?
Not that hard to learn, I think. You know, I started working industrial robot initially at SpaceX and then at Relativity. I think they're pretty intuitive. I think once you start asking it to do things that are outside of what they're supposed to do, that's gonna get tough, right? You know, like for us to sync these 2 robots to the point where they are actually accurate, that we cannot rely on the original software stack that comes with it, that's when it gets a little bit tricky. But the actual robots, they've done a very good job. I mean, it's very easy.
Good user interface?
Yeah.
all right. Are you ready for some robots to start moving?
Yes, sir.
All right, first they're gonna go into sort of a start position. And then I'm gonna start the path.
So this is going to the, you're going to the next part.
That's right, yeah, I'm starting on the first layer of the next part. So it'll sort of hover over the spot and then come in and then start moving. There's a lot of flop in the sheet too. Yeah, that's all right.
Ed, what do you call those dimples that I'm hearing? That noise, what is that? That's the plate moving.
That's the sheet, yeah, buckling in and out because the boundary conditions are loose about that part. So those are the things you need to account for when you're adjusting for the accuracy.
I see.
Right? So when you form the part, when you scan it, you figure out, okay, these are the areas that we're off, these are the areas undershoot, these are the areas we overshoot, and then you adjust for it for the path, and then it counts for this kind of loose movement in the sheet.
That's awesome.
Once you have, to your point, once you actually have a little bit of depth, gives it a little bit of stiffness, then it becomes much more stiffer and doesn't move like this.
Oh, wow.
So that's why a lot of parts have a little bit of skirt in the beginning. There's a little bit of portion that like you form into, gives it some stiffness. Now you have like what we call a bathtub to actually form the part in, right?
So you're localizing the rigidity
Right, yeah.
by making a, like, kind of like an I-beam
Yes,
locally.
Yes, like a little kind of like, yeah, basically an I-beam, yep.
Yeah, so it's not popping anymore.
Yeah, so it created a little bit of stiffness there, so no pop. Still moves a little bit, but yeah.
And that takes a pretty long time for that feature to be printed, right?
That whole thing takes 90 minutes.
Yeah, got it. And you guys are going to leave all this, right?
Oh yeah, we typically leave things running overnight all the time.
So you run lights out.
Yeah.
Yeah, that's awesome. Sweet. You know what we could do? Is I could just leave that GoPro here.
I'll ship it to you.
Yeah.
Satellite half domes.
Half domes?
Half
Like
dome with two
hemispheres?
yeah, hemispheres. Yes.
So what is the surface? What is the thickness across?
This actually gets pretty thin. So I think we started 2 millimeter. And here you're probably 0.4.
0.4?
Yeah.
Pretty. Oh yeah. So on the highest angle you get.
You get pretty thin. You can see this one actually failed.
So on a. Oh, I see. How did you catch that?
I think they CTDs. I mean, that one is visible, but I think many of these got CTs.
Oh, that's interesting because when you're doing pressure vessel calculations, you assume a uniform thickness,
Yeah.
and you don't have it.
You know, so we need to make sure that we get to minimum at least something that they're comfortable with.
Yeah. That's an interesting geometry there.
Yes. So the reason I actually put it next to that, they can kind of see the sections in the other one.
It's an annulus.
So there's like basically an annulus that comes together. There's 16 sections that come together and then you can form a toroidal tank.
That is so cool.
Yeah.
That's amazing.
This is just a demonstration, so it's manually TIG welded. So you got some like deformation as you're TIGging.
Oh, I could see the future. Like if you had multiple robots holding them in position and you had a robot welder.
Yes, you could then weld it after you form it. Also, our goal is to get to a point where we can just do this in 2 sections, top and bottom, through that restriking operation. Then we can also distribute the thickness a little bit better. So you kind of form it, instead of forming the water line, you form it like this. And then these tanks, NASA used to make them with bump formers back in the 60s for satellites. It's like a very efficient design for satellites because it's very volume efficient. Right?
Really?
Instead of having spherical tanks around your satellite, which is easier to make, but then you don't take advantage of the full volume, you can have a full tank around the satellite.
Really?
Yeah.
And a pass through for electronics and stuff?
Right.
Wow, I wonder if NASA's smart. I wonder if it has something to do with like solar loading on one side of the satellite or the other so you keep the fluid the same temperature. They're smart.
Yeah, but it was very hard to manufacture.
But you did it like this and you had support on each side. Do you call it support?
We call it a skirt,
Skirt.
but yeah, it's basically same as, effectively it's a support. Yeah.
That's cool.
Yeah.
So you have a laser scanner on there to verify the geometry.
Yes.
You ever have a laser cutter or anything?
Yes, so we don't do laser cutting today. We might add it in the future. Right now we do mechanical cutting. So using a spindle to cut the part out.
Safer.
It's safer and also it just preserves the material properties. Like you don't have heat affected zones as you're cutting. But then it doesn't give you as good of an edge quality. So with laser you get a very good edge quality, but you might have heat affected edges.
You've done a lot in your life in a short amount of time.
No, thank you.
Yeah.
No, I was excited. I think I was excited I was lucky to be friends with a lot of smarter people. I got involved with a lot of projects.
That's a very humble way of saying that.
Yeah.
Where did you go to school?
USC.
USC?
Yeah.
They have a good engineering program there, computer science?
Computer science is good, I think. But also I had like a very unconventional background. I left school so many times to go work. Because I always felt like, as long as if school is not going to let you work,
Yeah.
what's the point? So I left a few times. I left work at Microsoft for a couple of years. And then I worked for Google for a little bit. Then I went to SpaceX and really liked it. So I left grad school to just join.
So you didn't really focus on the end, like the piece of paper at the end.
Yes.
You focused on the actual education.
Right.
And you said, oh, well, the limits of my education are I'm not getting hands-on time. So you just went and got it.
Yes. I mean, if there was an opportunity for it to actually get stuff done and do it and learn, I think I always took that opportunity. It's just you know, until you end up doing, like I said, I always know it's like there are so many things you don't know unless you start doing it, and that's when you kind of learn it. Right?
So what would you say to a young person right now that's coming out of high school and they're interested in robotic manufacturing?
I think
Roboforming is a unique subset of robotics, industrial robots.
I think they should just start, you know, joining the projects that are doing these things, right? I think intern early. Just make sure in your school you intern early. You need to still have a good foundation, but now you can learn foundation anywhere. You can even watch your videos and learn some of the foundation, right?
the video you just made.
yeah, exactly. So I think that's just the beauty of it. Right now you can just decide what you like and go learn whatever you need to learn while doing it, right? Go find the people who are doing that, join them, and meanwhile learn everything you need to learn, and you know.
So don't necessarily get caught up in the traditional education system
like
if it's not right.
Assembly line education, get this and get this, and then go to work,
Dude, I'm impressed with you. You're an impressive dude, man. Thank you so much.
Thank you.
Yeah.
Yeah.
Okay, we came to another room. What is this?
This is our post-processing room. So this is where we basically, once the parts are done, we bring it here, clean it out. You know, we cut the tabs that you might have in the part.
And that's what I want to see here. So we've cut these tabs. I notice you insert and then you go along here. What is the methodology here? I notice they're kind of interesting. So is that a function of the robot path there? The tool path?
Yes. So basically the robot comes in, cuts it, leaves some tabs, and then in the end you kind of cut some tabs. You can see kind of the sheet moves slightly, and those are the spring back accommodations.
Residual stresses.
The residual stresses, right? So when you're forming the part, you actually have to form the part slightly different than what you think you're going to end up getting, and then in the end it kind of shrinks a little bit, and then you're going to get the robot butt.
So you accommodate for this?
Yes.
Oh, that's interesting. And so once you make that cut, you're done. And so you're not gonna, you'd have to rescan it if you had any other processes after the cut, but you don't care. You're gonna come in here and jigsaw that out.
What's exciting till now, like we couldn't do with stamping, is that, you know, you couldn't do a whole lot of different designs because for every design you have to make a new mold, right? So with our process now you can make very intricate designs of sheets that you can kind of put them in a sandwich structure. Like you kind of stack them up against each other, maybe you rivet at certain points. And now, for example, all of them together can look like a wing, a shape of a wing, but this wing is super performant because it's very light, but because of the structure of those sheets that were inside of it, becomes really rigid, right?
So you can optimize the structure, whereas you were, like in an airplane, you used to have you were limited by the type of material you had to create a longeron or something inside the plane. You can create a customized, even AI optimized part.
That's the key, right? Now you can actually iterate on it and you say, okay, give me 5, 6 to 10 different sheets that are specifically optimized for this application. The robots will form it, and then maybe you want to change your criteria and optimize it for another application, and the robot will form a different one, and the computer comes up with these designs.
I can even imagine a future where you would build a wing, you would have the different structure that you're describing inside, and you load test it.
Yes.
And because you could do it in 3 days, you build 4 wings with different optimized structures, and you see which one breaks at what load.
Absolutely.
Oh, that's cool.
Or you can capture so much data and then train these models, choose the data to train the computer to come up with the most optimized model too, right? Yeah.
Yeah, the old test and evaluation model test model loop.
Because you can generate parts with our process faster than you can simulate it.
Yes.
So that's what I think. Like computation.
Say that again. That was huge.
You can form parts faster than you could simulate it on a computer, right?
That is such a big deal.
Yes. So you're not, like, even the computation is slower than forming parts in physics, right? So with our process.
Thank you so much for watching this, the second channel here on Smarter Everyday 2, I guess is what we call this channel. But yeah, this channel's pretty cool. I get to go deep into the details. It's really, really cool. If you're watching this stuff, you're obviously a very intelligent person, and I'm just glad that you're here because I'm learning on all this stuff, and I'm excited that you're excited to learn with me. So anyway, if you'd like to consider subscribing to Smarter Everyday 2, that would be amazing because it's kind of like slowly, this channel is like the slow, steady channel that could. It's just like slowly growing, which I think is really cool. So if you'd like to check that out, feel free to consider subscribing. If not, no big deal. I am Destin. I'm just grateful you're here. Have a good one. Bye.